Look at the density of these storm clouds gathering along the coastline. This is the physical onset of the southwest monsoon. Within hours of landfall, millions of gallons of water crash down, instantly saturating landscapes that have baked in the sun for months. This map tracks precipitation. Entering through Kerala and pushing northward, it delivers 70% of the region's annual rainfall. This predictable pattern perfectly fills three critical sectors: sustaining agriculture, replenishing drinking water, and driving hydroelectric power. But over recent cycles, that historical predictability has fractured. The temporal progression of the monsoon is slowing down. Over this satellite view of the southern landmass, we can see the problem. The system is stalled. Today, we are going to trace exactly why these marine atmospheric shifts occur and track how an oceanic delay cascades into massive agricultural and economic volatility on land. What we are looking at is an active, systemic shock to one of the world's most vital supply chains. To understand the delay, we have to pull back from the land and look at the staging grounds, the Arabian Sea and the Bay of Bengal. This model demonstrates standard monsoon progression. Consistent winds act as an engine, pushing heavy moisture inland. Watch what happens when localized pressure drops emerge. As the clean wind vectors hit these anomalous zones, they fracture. The directional momentum required to drive the monsoon forward collapses. Instead of moving inland, the energy gets trapped out at sea, generating chaotic, swirling cloud formations in the upper atmosphere. We can observe this phenomenon directly. This satellite capture displays a severe, concentrated cyclone over the ocean, hoarding the moisture that should be traveling toward the mainland. These highly localized marine pressure drops essentially steal the kinetic energy required to sustain the monsoon's forward velocity. As a result, millions of tons of water remain stalled over the ocean, throwing off the expected timeline of the rains on land by weeks. Historical weather models fail precisely because these erratic, localized marine anomalies actively break the standard wind patterns. The engine behind this increasing volatility is global climate change, acting as a macro amplifier for these marine anomalies. Instead of a reliable seasonal cadence, regions experience wild extremes. Entire planting cycles are wiped out by intense droughts that turn arable soil to dust. When the rain finally breaks, it often arrives not as a steady cycle, but as a violent deluge that floods infrastructure and drowns crops. You cannot plan an agricultural economy around wild swings between total dehydration and total inundation. Global climate shifts multiply the baseline risk, replacing the predictable rhythm of the monsoon with highly volatile, highly localized destructive events. Let's transition from the atmospheric data to the literal ground level to see how this impacts a farmer's yield. When the rain is delayed at sea, farmers are stuck. Preparing hardened, moistureless fields is grueling and inefficient, forcing them to pause their entire operation. This Gantt chart outlines an agricultural cycle. The most critical metric here is the optimal sowing window, a specific biological timeframe tied to historical monsoon arrival that guarantees maximum yield. Look at how this delay distorts the timeline. As the actual monsoon arrival pushes right, the optimal sowing window severely compresses. The downstream biological effects are severe. Late planting pushes the crop's vital vegetative and reproductive stages straight into higher temperatures and peak pest seasons. The plant is fighting against an aggressive environment from day one, struggling to establish root systems in hardened topsoil. This temporal compression caps the potential of the plant. It degrades the final crop quality and slashes the total volume harvested per hectare. Agronomic timeline compression dictates that a weather delay in the sky guarantees a compromised harvest on the ground. We can now map that biological failure directly into the macroeconomic level. When total yield volume per hectare drops, rural logistics networks grind to a halt. There simply isn't enough product to load into the trucks. This models a healthy supply chain. High yield ensures thick streams of commodities flowing into central markets. Apply the yield drop from a delayed season, and the network starves. Farm nodes shrink, and the volume of goods moving along these routes dries up. The immediate result of reduced agricultural output is a severe scarcity shock at the distribution level. That scarcity is passed to the consumer. With fewer vegetables hitting the market stalls, supply and demand exerts violent upward pressure on food prices. A meteorological anomaly in the Arabian Sea actively inflates the daily kitchen budget of millions of families. Given this rigid cascade of failures, strictly relying on historical farming calendars is a major vulnerability. To survive, the agricultural supply chain must shift to dynamic temporal planning, abandoning strict dates in favor of live meteorological triggers. Modern meteorology provides exactly this capability. By actively tracking the development and dissipation of marine anomalies, analysts can accurately predict exact, localized onset windows. Because a delayed monsoon can accelerate rapidly once the wind patterns clear, farmers ready to deploy instantly on a targeted weather trigger can still maximize their optimal sowing window and secure a healthy yield. Maintaining agricultural survival now demands executing rapid, data-driven responses to live atmospheric intelligence. Let's review the complete mechanism. Localized pressure drops over the ocean scatter incoming winds, physically stalling the monsoon. As the delay extends, the optimal sowing window forcefully compresses, missing ideal timelines. Lower yields systematically starve local supply routes, translating this stall directly into consumer inflation. Protecting the agricultural economy from these shocks requires decoupling from rigid historical schedules and deploying resources with absolute agility. As global climate shifts make weather patterns increasingly volatile, maintaining our food supply depends entirely on dynamic, real-time adaptation.